let's go to chapter 30, which is inductance. The symbol is L. Let's continue in the analysis when the magnetic field is changing in one point. And we have these cases. When we have a magnet moving down, correct? At this point, we have a change in the magnetic field, right? And we create or induce an electric field. Also, right, imagine that this is the magnetic field, and the magnetic field is increasing. Then every time we have a change, remember, in the magnetic field, we induce an electric field. Also, we know that we have a current, could be a constant, the current is constant, so we have a magnetic field produced by the current. We know that. Also, if the current increases or changes, right, we have a change in the magnetic field, correct? Now, let's see what happens when we have two coils, and one of these coils is with some current at the beginning, right? It's like when you turn on your lights in your room, right? At the beginning, there's not current, but later we have the current increases, and then the current stays constant. In this interval where the current is changing, correct, we have a changing magnetic field. Every time we have a current, we create a magnetic field. But if the current is increasing, we have an electric field, correct? Or also we can see that the magnetic flux is changing. If the magnetic flux is changing, we can relate that to the electromotive force according to Faraday's law. Perfect. Imagine again, this is the case, we have a change in current produced by this coil with N turns. This is coil 1. Close by, there is another coil, right, with numbers of turns N2, and the changing magnetic flux produced by coil 1 goes through coil 2. Perfect. So that simulates the situation right here, right? The magnetic field, flux is increasing. That happens right here. So when that happens, well, we have what? We have a electric field, or we can relate it later to electromotive force. Correct? Perfect. We know also, right, that if the current on coil 1 increases, also the magnetic flux through this coil is increasing too. Perfect. Now, from here, we can see that if this magnetic flux is increasing, right, or is proportional to this current, and the current is increasing, means what? Well, in this case, we have that this magnetic flux is equals to, remember, we need to eliminate this symbol using a constant. The constant is used to match the unit in general. Perfect. Times what? M to 1 times current 1. M, this is the constant of proportionality, is called the mutual inductance. M, mutual inductance. Okay, and this is, again, the mutual inductance done on object or coil 2 by coil 1. Correct? Perfect. But we are interested on the electromotive force. Okay, let's continue. In this case, also we can multiply this by n, correct? And we create the same effect because we're dealing with the numbers of coils too. Perfect. Now, let's again introduce the Faraday's law. It says that the electromotive force that is induced, in this case in coil 2, must be equals to negative N2, correct, times the change of the magnetic flux, correct, respect to time on this coil 2. Correct? When we produce this right here, right, make the derivative right here, we find that this is equals to negative the mutual inductance times the derivative of current 1 on coil 1, correct, respect to time. Perfect. And that's gonna be then the mutual the electromotive force induced on coil 2 equals to negative mutual inductance, correct, times this change of current in coil 1. Correct? Perfect. Now, from here also we can solve for mutual inductance, right? Mutual inductance is equals to, we can do it from here. So now we what? N magnetic flux through coil 2 divided by what? Where am I? Right here, divided by I, right? Current in coil 1. Actually, ladies found that we have now the current in this coil, and we're looking for the induced electromotive force in the first coil. Well, it's found that we have the same relationship, right? Means that the mutual inductance on coil 2 due to coil 1 must be equals to the mutual inductance in coil 1 coil 1 due to coil 2. Right? They're the same. The same. Perfect. Now let's go to the unit. We need a unit. The unit for mutual inductance. The unit for mutual inductance or for inductance in general is the Henry. Right? Unit. Right? Henry. So 1 Henry, if we are going to the definition for mutual inductance, equals to the unit of this magnetic flux is Weber, right? Divided by the amps, which is the unit of the current. Also, this is equals to voltage times second divided by the current. Also, this is equals to volts second divided by amps, correct, or joules divided by amps square. So that's gonna be the units for Henry, which is the unit of the inductance, correct? Perfect. Now let's go to self-inductance. We found already right here mutual inductance. Now let's go to self-inductance. Great. Let's do it. Self-inductance. That's the case when we have one coil, right? One solenoid or solenoid. The coil or solenoid is called the inductor. Imagine that we have this circuit from the beginning to visualize it, right? This is open at the beginning, right? And then we have a coil right here. It looks like the coil. Okay, looks like it goes like this. Imagine, and then we have a resistor right here. Correct. That's the symbol for coil. It's the symbol for resistor, or for the inductor, right? And resistor. We have, of course, the battery. Perfect. Now, what happens when we close? When we close the circuit. When we close the circuit, we have current going in this direction, correct? Perfect. But we know from the previous analysis, every time we have a coil, right, coil produces, like in this case, a magnetic field. And according to Faraday's law and Lenz law, according to the sign negative, remember, the magnetic field produced by the current is going to be in opposite direction as the incoming changes of the magnetic field. Because right here, this current is changing. The current is changing produces a increase, in this case, in this coil. The increase in the coil produces a magnetic field that is opposing, right, the beginning magnetic field, correct? That again is represented by this symbol negative, the Lenz law. Perfect. Means what? Means that this behaves as a battery acting right in opposite direction, correct? And this is called, right, the back EMF or the induced EMF or back EMF, correct? Perfect. Now it's gonna be the induced EMF. It's also called the back, right, EMF, correct? Now, the same thing as before, we find that this magnetic flux is proportional to the initial current, right? Or the current right here, correct? I remember the current is changing. Perfect. So let's eliminate this symbol. And what do we have? We have that this magnetic flux is equals to L. Now this is the self-inductance. Remember, we're dealing with self-inductance. The symbol is L. Okay, times the current. Perfect. One more time, you're looking for the induced, right, electromotive force. Great. And the same thing as before, where we can multiply by numbers of turns right here. And then what do we have? Well, let's apply the Faraday's law. And what do we have? It's equals to negative the numbers of loops or turns, right, times the change in the magnetic flux, right, respect to time. And this is equals to, it's going to be equals to negative L, the self-inductance, times the I over dt. It's similar to when we have mutual inductance. So one more time, this is the induced, right? We can use this symbol, right? L that represent, right, the self-inductance, the induced, right, electromotive force, like in this case, correct, is equals to negative the self-inductance times the I dt. Correct? Perfect. Now, what happens when we have these inductors in series or in parallel? Well, when we have inductors in series, right, the total inductance in series is gonna be inductance 1 plus 2 plus 3, right, and so on. This is in series. Or when we have this in parallel, when these are in parallel, what do we have? This is equals to 1 over L1 plus 1 over L2, right, and so on, plus 1 over L3 inverse. This is in parallel. And you can see these are similar to resistors, right? When we have resistors in series, behaves in this way, and when we have resistors in parallel, behaves very similarly to the inductors. Also, we can say that the inductor behaves as a resistor too. Okay, but more general, it behaves like a battery, like in this case. Perfect, perfect. Okay, now let's make a summary on this analysis. In general, when we have current, and we have the inductor, okay, that's the symbol for inductor. Imagine we have another one right here, correct? In this way, imagine that we're current in this direction, In this case, it goes from positive to negative, and right here it goes from negative to positive. Correct. In this case, we have that the current increases. If the current increases, right, this is the current. So we have a electromotive force in opposite direction. Means this behaves as a battery, correct? In this way. What happens if the current decreases? Well, in this case, the induced voltage, right, goes in this direction, parallel to the current, means that it behaves as a battery, correct? In this way, negative, positive, this is positive, negative. Correct? So this is like inertia, right? If an object, if the current it's accelerating, right? Is increasing. There is a tendency to keep the current, let's say, at some value constant, right? If it's decreasing, the action for the inductor is opposite, right? To keep the velocity, let's say, the change constant, right? That's another idea to represent the behavior of the inductor. Okay, perfect. Now let's go to circuit. Now let's work with Kirchhoff's rules when we close the circuit, right? Let's see what happens. Try to find a the current, right, in function of time when we close the circuit and when we open the circuit, right? Because we mentioned that this current is not constant. At the beginning is zero and then reaches the maximum. We're looking for the dependence of the currents in the timer. How long it needs, right, to reach, let's say, the maximum value for this current. Okay, let's do it. Let's do it. In this case, we have the RL circuit. Right? We have the RL circuit. The RL circuit. So we're dealing with the resistor and the inductor in the circuit. So imagine that we have this circuit. So we have right here a resistor. Also we have right here a inductor, correct? Like this, in this way. At the beginning, this is open, the circuit is opened. Also we have right here the electromotive force, correct? Perfect. Perfect. Again, this is the resistor and this is the inductor. What happens, this is the switch right here. What happens when we just close, right, the circuit, correct? And well, let's do it. Let's use Kirchhoff's rules, right? The loop rule to see what happens. Okay, let's do it. Imagine that we close this circuit, so we create a current through this in this way, right? The current goes from positive to negative, right? In this way, in this direction, correct? It's positive to negative. Okay, great. So what do we have? Well, according to the loop rule, we have that this electromotive force minus the current times the resistance minus the current times well, right here, what do we have? Look, in this case, we're looking for, remember, this produces electromotive force, voltage. We need also the voltage right here, but what is the voltage that we found for the inductor? Is gonna be this one, right? Minus what? L or di dt equals to what? Equals to 0. Correct? Perfect. Now let's see. Let's solve for the I dt and see what happens. Okay, so the I, this rate, right? The change in current respect to time is equals to what? Is equals to the electromotive force divided by the inductance plus resistor divided by the inductor times the current. Okay, now let's see what happens when at the beginning the current is 0, right? If the current, right, is 0 at the beginning, so what do we have? Well, we have that this rate, this change in the current respect to time is just equals to what? equals to the electromotive force divided by the inductor, right? At the beginning, why we have only this part, correct? Electromotive force divided by the inductor. Perfect. What happens at the end? What happened at the end? At the end, when at the end, remember at the beginning we have the current increases, but at the end the current is constant. If the current is constant, this change becomes zero. Correct? Perfect. So at the end, when this change is equal to zero, means there is no more change. Now the current is constant. Correct? This becomes zero. And then what do we have? We have that zero must be equals to electromotive force over the inductance plus R over L. Am I right here? Is this one correct? Is this one correct? It looks like it's gonna be negative, correct? It's gonna be negative. This picture, yeah, it's negative. Thanks, it's negative, it's negative. Okay, so it's gonna be negative, correct? R over L times the current. Means what? Means that the current at the end is equals to the current at the end, because it's constant. We represent that, right, by this capital I. Usually capital letters is for constant, and when they are changing we use little, right, the small letters. Okay, perfect. Equals to the electromotive force divided by the resistance. You know that, right? When we have a constant current, well, using Ohm's law, it's gonna be voltage divided by the resistance. Correct? Perfect. Okay, these are some conclusions that we got. Now let's integrate this equation. Correct? Let's arrange it in this way. In this way, we divide this by L. Correct? Or by R, we divide this by R. Look, by R, and by R. And then what do we have? It's equals to electromotive force divided by R minus, right, this current minus L over R, right, this change. Okay, perfect. And then when we arrange it, we'll get this equation, the I over I minus electromotive force times the current, correct, must be equals to negative R over L, correct, dt. Now let's integrate from 0 to some I, right, from 0 to some t. Okay, and when we do the integral, right, this is equals to ln, correct, of 1 minus electromotive force divided by R divided by negative electromotive force divided by R is equals to negative R over L times T. Now let's use the anti-log, right? And what do we have? Well, we have at the end that the current in function of time, the current any time, in this case is equals to the electromotive force times the divided by the resistance times 1 minus E, right, 2 minus R over LT. Right, and this is the case when the current is going in this RL circuit. Correct? Perfect. So it's equals to electromotive force divided by the resistance times 1 minus E to the negative R over LT. Correct? Perfect. Now, in this case, this quantity R over L is equals to tau, and this is called the time constant, right? This is the time constant. What is the meaning for that time constant? Well, this is the meaning for this time constant. The meaning is if we have this graph right here, and this is the current, changing current, correct? This is the time, and this is the maximum current, which is maximum current is electromotive force, right? We found the force divided by R, correct? What happens when it decreases? Again, actually gonna be the maximum because it's increasing, right? Increasing, right? It's gonna be correct in that way. Now at this time, tau, the current is right here. The current is right here. Is equals to, what is equals to this equation? Right, right here, and it's found to have, right, this value. This is tau, and this is actually 0.63, and the value of the torque current at this time. At this time, we got this value of the torque current. The torque current, remember, is constant, the electromotive force divided by the resistance. Correct? Great. Now let's see the other case when we disconnect, right, or open the circuit. What happens then? Okay, let's do it. Let's do it. Let's do it. As you can see, this is similar to the case where we have a capacitor, right? When we charge a capacitor and when we discharge a capacitor. Great. Perfect. Now let's do the other case. Correct. Current decay. This is called current decay of a RL circuit, right? RL circuit. Okay, perfect. The same thing. Before, imagine one more time. This is the battery right here. We have an open circuit, right? And we have this connection right here. We have another switch right here. Correct? Imagine. And then we have the inductor, and we have right here the resistor. Correct? In this way. This is electromotive force. This is switch 1. This is switch 2. In case 1, when we are dealing with going the charge, correct? We just close this circuit. Well, imagine that's the case, the previous case, right? When we close the circuit, well, we create, right, we close the circuit, we create this, the current is moving correct in this direction, current. Now, let's do it this way. Let's open the circuit, and at the same time, let's close this switch. In that way, right? It's like that. Now let's do it in this way. Perfect. And then what do we have? Well, in this case, we call this the current decay. The current decay. Let's do it. Let's use again the Kirchhoff's rules. And what do we have? Well, we have, this is the resistor, this is the inductor. So we have that negative, the current times the resistance minus, right, this, we can call it a voltage drop, right? Voltage drop right here, which is equals to L di dt and equals to 0. Correct? And we can rearrange it, correct? And what do we have? We have di over I must be equals to negative negative R over L, correct? That's correct. Perfect. Times dt. And then we integrate from 0 to some I. We can differentiate by make it prime from 0 to some t. Correct? Perfect. Actually, gonna be R naught right here. There's some I naught. Perfect. And what do we have? This is ln, correct, of some current right here, initial current equals to a negative R over LT. Now applying the integral, what do we have? We have that current at any time is equals to current at the beginning times what? Times e to the minus R over L, correct, times T. But we found that it's equals to the, we found before, right? At the beginning, is equals to, this is the electromotive force divided by the resistance. So what do we have at the end? Gonna be that current at any time is equals to electromotive force when we have a current decay divided by the resistance times e to the negative R over L times T. Right? And in this case, this is the behavior. This is the behavior for this current. One more time. This is time, right? This is the current. This is at the beginning. The current is equals to electromotive force divided by the resistance, and then of course, right, decays in this way. So at this time, at time tau, one more time tau, the time constant is equals to R over L. In this picture, correct, this is gonna be tau, right? This is the current at any time. And at this time, correct, the current is at 0.37, the maximum current. The maximum current. Correct. Perfect. Now let's go to the energy stored in an inductor. Let's see how we can find that energy. Let's do it. Energy stored in an inductor. We found before that this electromotive force is equal, we use, right, the Kirchhoff's rules, is equals to current times resistance plus the inductance times the change in the current respect to time. Right? Now what happens if we multiply this by the current? So it becomes this relationship, right? And it'll be inductance times current, di dt. In this case, this is the power supplied by the battery, right? Power, this is power supplied by the battery. And so this is the power dissipated by the resistor, right? Power dissipated by the resistor. And this is the power supplied to the inductor, right? This is the power supplied by battery. This is the power supplied to the inductor, right? Power supplied to the inductor. Correct? Now, how do we define power? Power, remember, power is just energy divided by the time. Correct? So we have power is equals to, what is energy right here? We're dealing with, remember, the energy stored in an inductor. So we have to work with this term right here. So now the energy of the inductor, right, with respect to time, that's the change, correct, must be equals to what? Must be equals to the inductance times current di dt. Correct? From here, what do we have? Well, that this energy stored in the inductor is equals to, remember this is cancelled, dt, probably gonna be the inductance times I di. Now let's integrate. When we integrate, what do we have? The energy stored in the inductor is equals to L I squared divided by 2. Correct? Perfect. and that's gonna be the energy is stored in a inductor. It's gonna be 1/2 of Li squared. But in general, it's easier in this case, as we did for a capacitor, to use the energy density. Okay, the energy density in an inductor, or in this case in a solenoid. Let's use a solenoid to be the inductor. Okay, for a solenoid is found that the inductance for a solenoid, the inductance is equals to mu naught n square area times L. Right, and also for the inductor, it's found that the magnetic field is equals to mu naught, correct, times N times the current. Now let's look for energy. So energy of the inductor we found is equals to 1/2 L inductance times I squared. Now let's substitute these values right here. And what do we have? It's equals to 1/2 times what? Times L, which is mu naught n square area L, the length, right, of the solenoid, correct, times what? Times mu naught. Let's solve. From here, let's solve for I. The current is equals to B divided by mu naught n. Okay, so right here we have that this is equals to B mu naught n squared. And what is this? Well, this is equals to B squared, right, area L over 2 mu naught. But look, for a solenoid, remember it's a solenoid. For a solenoid, this is the area and this is L. When we multiply these two, area times area equals to the volume of the solenoid, correct? Now from here we have that the energy per unit volume, which is volume, is equals to B squared over 2 mu naught. This is just the energy density, correct? So energy density for the inductor, right? Energy density is equals to B squared over 2 mu sub naught. Okay, and let's stop right here. This is half of the chapter. Okay, we start in the energy density for a inductor, taking the inductor to be a solenoid. Okay, great. See you in the second half for this chapter. Thank you. Bye.